And then what we need to figure out is you guys need to join the right classes on the College Board. We've done that in other APs. Okay, so where do we go? Because that's the part I can't remember.
If you go to College Board, there's one place for AP and you go to AP.
Okay, so let's try that. So if we go to, has everybody done another class this year already? Okay, I'm laying on can't make it that. There's one of those 3 o'clock in the morning. Oh my God, we haven't done this in the city. Do that. AP Physics, if you want to, your code is up there too at the bottom. And you can do that now as well, and we'll just catch yes and Lauren on Monday.
Which one is it?
No, that's okay. The top one is AB, the middle one is BC, and the bottom one is AP Physics.
If we are BC, should we also go AB?
Yeah. So we need that travel to people. And yeah, that is right. Yes, she can press that. Okay, so everybody join the things they need to join for me. You could if you want to, that would be fine to you. Okay. All right, then let's get going. I'm going to wait to submit my attendance so that wanders in. All right, so implicit differentiation. There we go. Which is really just an application of the chain rule, which is why we need to do the chain rule first. I find that implicit differentiation makes finding the derivative of inverse trig function easier, which is why I split the 2 sections. So depending on how far we get today, and how comfortable you are with implicit differentiation, we may do derivatives of inverse functions on Monday, and we may get into Wednesday. Kind of depends on how today goes. All right. So implicit differentiation helps us to find dy dx, the derivative, however you want to put it, when we don't have y equals something. Okay. So not all equations can be expressed as y equals. Sometimes they can, but it's a real pain in the butt to go back and solve that equation for y. And then you end up having to do a whole bunch of really weird and wacky derivatives when you could just use implicit differentiation. All right. So, are there questions on the checkpoints? Yeah. 3.48. I have the, okay. So we're going to do checkpoint 3.48. And we've got 4x to the fifth plus tangent y is equal to y squared plus 5x. Right? Is the equation?
Yeah.
Yes?
Did you guys see the calculus? Yeah. I got 100.39. But it's 10.3.
3.49. Oh, I'm sorry.
Yeah, it's just, the textbook, it doesn't have source 24. Yeah.
What is the textbook do?
No, it's just on the reading guide, the 3.48.
Oh, you just have to fix that and do the next one in order.
Yeah, so the 3.48, I meant to say 3.49.
Okay. Because I cut and paste and then occasionally I forget to change the number. So y'all should just
Yeah, it was just the last one.
use your common sense. Yeah, I'm surprised you didn't write to me and tell me that I messed it up. All right, so that's 3.48. You want 3.49. Okay, no, that's cool. Okay, so 3.49 is x squared minus y squared is equal to 6. Okay. So when we try to take implicit differentiation, and yes, you could do this. You could solve this for y, right? Y is going to be plus or minus the square root of x squared minus 16. Right? So we could, and we could do the chain rule and stuff. But we want to try this implicit differentiation. So there's kind of 3 different types of terms you can get when you're doing implicit differentiation. The first one is when it's just a function of x, like a regular old term, and then we just take the derivative the way we always have. So what's the derivative of x squared going to be? 2x. Okay. And then when I have a term that's only a function of y, there's kind of 2 different ways to look at it. There's a here's the rules way to look at it, and there's a here's why it happens way of looking at it. Okay. So when I'm taking the derivative, and this is another reason why that Leibniz notation is important, is what I'm really doing is taking the derivative of something, anything, with respect to x. Okay. So when I look at this y squared term, that's a composite function. It's something that's squared, but I also have to take the derivative of that something. So it's really applying the chain rule. So what I do is, because it's something squared, I bring down my 2, I take my something, I raise it to the 1 power. But because that something isn't an x, I have to apply the chain rule and take the derivative of what's inside. So what's the derivative of y? dy dx. Okay, and that's kind of the why of why we do it. Oh, I see. I figured out that's the problem. I can do derivative of 16 plus 15. Okay. So that of course is going to be equal to 0 because when I have a constant term, it's not 0. That's what I mean to talk. Okay. So now what I do is I solve for dy dx. So that's going to give me 2x is equal to 2y dy dx. I can cancel my 2's. Dy dx is going to be x over y. Then I think we're supposed to find the equation of the tangent line to the point.
Yeah, the point is
5.3. Okay. So if I evaluate this at 5 common 3, I'm going to get 5/3. And then it's just going to be y minus 3 is equal to 5/3 times x minus 5. And that is here. Okay, and then you can do some math, right? You need to, but that was on me. Sorry. I make mistakes all the time. And there were really only like this two checkpoints, right? Okay. All right. So I feel like you should do some more examples. Yes? Yeah.
For the checkpoint 3.48, in the video, you write the answer for the you write answer like 20 x to the 4 minus 5, but for the answer you write down under it, if you say 20 x to the 4 is 12.
Oh, it should be minus 5. Okay, fine. It should be minus 5. Okay. All right. So let's do some more examples. Okay. So you should have a bunch of these written down, right, in 3.8 class time. So I think that's the next one. X cubed plus y cubed is equal to 18xy. So I'm not actually sure we can solve this for y. Not actually sure we can do it. Okay. So it's a perfect example again of where we want to use implicit differentiation. So my first term is just a function of x. So what's the derivative of the first term? 3x squared. Okay. My next term is just a function of y, like we were talking about. Okay. So what I really have to do is apply the chain rule. I have a composite function. I've got something cubed. Cubed is my outside function. Y is my inside function. So what's the derivative of 3y of y cubed going to be? Right. 3y squared dy dx. Okay. And then on the other side, I'm going to pull out this 18. I've got x times y. And so what I need to do is, it's a term that's a mix of x and y. And I need to apply whatever kind of rules I apply. So we were talking the other day about how like product rule and chain rule are kind of what we have to do first. So we need to acknowledge that I've got two functions that are multiplied by each other. And so when I have two functions multiplied by each other, I use product rule. So product rule says I write down the first term, that's x. And I take the derivative of the second term. So what's the derivative of y? dy dx. Plus, and then I take the second term times the derivative of the first term. And what's the derivative of x? 1. Okay. And then it just comes down to algebra. And I'm going to take all my terms that have dy dx's and put them on one side, and take all my terms that don't have dy dx's and put them on the other side. So this is going to give me 3x squared minus 18y is going to be 18x dy dx minus 3y squared dy dx. Check because I'm doing it in my head. Okay. So I still have my 3x squared minus 18y, and I'm going to pull out dy dx, factor it out to my terms on the right hand side. and then divide both sides by this. So I end up with dy dx is equal to 3x squared minus 18y over 18x minus 3y. Okay. So we feeling okay? Yeah?
Okay, so this is a really good question, but would dy represent 3x squared minus 18y?
No.
Okay.
Right now, and in situations like this, dy dx is the same. Single unit. It might look like it's a fraction, but it's not. Later on, that will change, but it still will not be the numerator that it's equivalent to. But for right now, dy dx, not dy divided by dx. Dy dx. Okay. Don't have to make this hand adjustment. Okay? All right, so once you try one on your own, there should be a worksheet in OneNote. That is not this. It should be differentiation, implicit differentiation. Okay. And you try number 6 now. Yep. Okay, they'll work on that. What?
That seems to be actually something wrong.
But if I take the derivative of 3x, should make
Oh,
it 3.
yeah.
Feels weird. Did I do it right? Deanna says yes. Glad you did. And are we on the same page now? Awesome. It was so much fun to meet so many friends here. Okay, so we feeling okay with this? Want to try another one on your own? How about number 9? Down yeah, I can't get that. So my OneNote is frozen, but it's okay because I have it figured out. So number 9 is 2x cubed is equal to 3xy plus 1 squared.
Is there one factoring 3x+? Like,
Oh, multiplying it out? You could, but I think it would be excellent practice for chain rule combined with implicit differentiation. Okay, so remember, you should really be copying down the way I'm doing it as much as checking it against what you do. Yeah, no, what's that?
should it be the 3x squared line plus
Which line are we talking about?
the third line?
This one here? This line?
No, the fourth.
What's the first term in that
X squared minus.
line? So this line down here right
Yeah.
before, okay, so what happened?
For the U line over here, should it be the
Oh, that should get plus. So change? Good, thank you. Okay. All right, are we good? Need to go through it step by step? Maybe? Let's try. Okay? So let's look at it again. Maybe we can just get it started and not worry about the algebra. Okay? Because I think the first line is the toughest. Okay? So on the left side, that's just a plain old power rule derivative, right? So that gives us 6x squared. On the right, though, it's a little more complicated. So I'm going to start with chain rule because I've got something that's not an x raised to a power. Okay? So when I do chain rule, I take the derivative of my outside function, which is the squared in this case. I evaluate it at my inside function, so I just end up with another 3xy. Okay? But then with chain rule, I have to take the derivative of what's inside. Okay? So I know that when I take the derivative of 1, I'm going to get what? 0. So I only have to worry about this 3xy. So I've got my 3, and what am I going to use for taking the derivative of x times y? Product rule, okay? Which means I take the first term, which is an x, and what's the derivative of y? dy dx, plus, I still have my 3 hanging around. When I do the second term of using product rule, I take my second term, which is y, times the derivative of the first. And what's the derivative of x? 1. Okay? And then everything after that is just algebra. Okay? Which you can slow down and do at your leisure. All right? Party.
It works for this time, but when I did it, I considered it like 3x. The first term of y.
That's fine. It'll work. It will work. It will always work. I mean, you can take that, like sometimes I take the constant and I factor it out. I do that if the thing my constant is multiplied by is complicated, because I don't have to worry about it. But I could make it 3x times y, and then I've got 3x times dy dx, plus y times the derivative of 3x is 3. So it will always work. That is a perfectly valid way. Okay? All right, so let's do a couple more examples together that kind of do some applications or places in which you may find this. The AP exam might say use implicit differentiation to find this answer, but it's more likely that they'll give you something funky. We've got x squared plus y squared is equal to 9, and it'll say it wants to know dy dx, or the slope at 0.0,3. So we're going to take the derivative of both sides. So Annabelle, what's the derivative of x squared? Good. Katie, what's the derivative of y squared? Excellent. Sophie, what's the derivative of 9? There we go. Okay. So I can factor out my 2 and cancel it, right? And I end up with y times dy dx is equal to negative x. Or dy dx is negative x over y. Okay, you good with this? All right. So if I evaluate that at 0,3, that's going to give me negative 0 over 3, or what? 0. Okay. So this is a nice problem because we can actually check our answer. What is x squared plus y squared equals 9 the equation for? A circle, Okay, so it's going to give me a circle that looks something like this. Okay, where's 0, what's the radius of my circle? 3. So where is 0, 3?
On the y.
On the y-axis, right? It's right here. What does the derivative mean again? The slope of the tangent line. What would you expect? What does the tangent line look at 0, 3? Right, it's horizontal. And what is the slope of a horizontal line? 0. Okay, so it kind of all fits together. All right. I think we have time for one more. Okay. So the next one is a little wackier. So this is the one that says find all the points on the curve x squared plus xy plus y squared equals 7 that are parallel to the x-axis, and the ones where the tangent curve is parallel to the y-axis, right? Okay, so let's start with part A, which is looking for the points that are that have tangent lines that are parallel to the x-axis. Okay, we just had a line, right, that was parallel to the x-axis. What's the slope of a line that's parallel to the x-axis? 0. So that means that we're looking for the places where dy dx is equal to 0. Okay, so the first thing we have to do is find dy dx. So find dy dx. Yours look like mine? Okay, good. Right, and I want to know all the places where that's going to be equal to 0. So of course, what I really want are all the places where the numerator is equal to 0. I don't want the denominator equal to 0 because then my stuff is undefined. And undefined isn't going to help me. So basically, if I look at this, what it tells me is a relationship between x and y. That this is going to work where my y values are equal to -2x. But the problem actually wants us to find actual values. It wants numbers. So what's kind of my problem here? How many unknowns do I have? 2, right? Because y and x, I really, unless I know what an x value is, then I can't figure out what y is. So if I have 2 unknowns, how many equations do I need? 2. I've got 1 right here, And where's my other one that pertains to this situation? So the original equation, okay? Any point, any set of x and y that I deal with has to be on the original graph, okay? So we can take y equals 2x and substitute that into our original equation, all right? So my original equation, I'm just going to write it down again, is x squared plus xy plus y squared is equal to 7. But then every place I have a y, I'm going to substitute in negative 2x. And now, how many variables do I have? How many unknowns? Just one. So I can solve for x. So you solve for x. Okay. Don't forget that when you take the square root, it's a plus or a minus. So then it's asking me for points, which means I need an x and a y, right? So I can recall, instead of substituting into this monster of an equation, I can recall that y is equal to negative 2x. Okay? So that means that 1 point is going to be positive radical 7/3, and my y value is going to be negative 2 times radical 7/3. And then I take negative radical 7/3, and when I substitute it in up here, that gives me positive 2 radical 7/3. Okay. Are we good? All right. Everybody good? Vivette, you good? Okay. Because part B is a little wacky. For part B, we're looking for the points where our tangent is parallel to the y-axis. Now, what's the slope of a line that's parallel to the y-axis? What is it?
Oh, I'm gonna sneeze inside my mouth.
But better than spraying my germs all over Fiona and the rest of you. I'd scare us. Okay, so what is it? What's the slope of a line that's parallel to the y-axis? What slope again? And don't tell me derivative. What slope? Change in y over change in x. What's the change in x for a line that's parallel to the y-axis? 0. So I've got whatever change in y I want, which is a number, over 0. So what's the slope of this line? What? What? Undefined or infinity. Okay? You were all making noise, but I honestly could not hear what you're saying. It's not making much. Okay? So I could take the derivative that I found and set it equal to infinity, which would mean I was doing what? Remember, I have dy dx is equal to -2 minus y over 2y plus x. And if I want to set that equal to infinity, how do I get infinity on x?
And 2y plus x.
So I might take, not to infinity, I might take the denominator and set it equal to what? 0. Okay. That would do it for me. But there's another way. So I've got my equation here, x squared plus xy plus y squared is equal to 7. Now, what I could do is, if instead of looking for dy dx, I was looking for dx dy, what if in my head I decided that x was a function of y instead of y being a function of x? There's no reason why I can't do that. Okay, this isn't an experiment where one thing is definitely the independent variable and one thing is definitely the dependent variable that I'm measuring. These are just points. Okay, so I can decide in my head that x is my dependent variable and y is my independent. And if that's the case, and this is still a slope, it's just a slope defined differently. What would the slope be of a vertical line? 0. Okay, because again, for a vertical line, what's my change in x? 0. Well, what's my change in y? Anything I want it to be, it's a number. Okay, so we could take the derivative of our original equation with respect to y. So I could take d by dy of x squared plus xy plus y squared is going to be equal to d by dy of 7. And I just write it out this way to kind of remind us of what we're taking the derivative with respect to. Okay. And now we're in class. Wait a minute, I know I had it working. 855. Okay. So let's go through this term by term and be really careful. If I'm taking the derivative with respect to y, what's the derivative of x squared? Dagny. Yeah. Okay. Because now x is that thing that's a function of y. X is my composite function. Okay. What am I going to use to evaluate the derivative of x times y? Product rule. Okay. So I'm going to take the first thing, which is x. What's the derivative of y going to be in this situation? 1. Okay. Plus y times the derivative of x, which is going to be what? Dx dy. What's the derivative of y squared going to be? 2y, and then the derivative of 7 is still 0. Okay. And then it's just algebra again. So I'm going to have 2x plus y times dx dy is going to be equal to negative x minus 2y, or dx dy is negative x minus 2y all over 2x plus y. Okay. And again, if I set this equal to 0, what I'm really doing is setting the numerator equal to 0. And if I multiply through by -1, what I really have is x plus 2y is equal to 0, which is exactly what we wanted to do originally. Okay, so it's just a different way to get to the same place. So I do the same thing I did before, which is to say that x is equal to -2y. We're going to substitute that back in to our original equation. So I'm just going to write that down again. X squared plus xy plus y squared is equal to 7. And I'm going to let x be equal to -2y. And everywhere I have an x, I put in my -2y. So that gives me 4y squared minus 2y squared plus y squared is 7. Or 3y squared is equal to 7, or y is plus or minus the square root of 7/3. Again, I'm looking for points, so I can substitute this into here and get -2 radical 7/3 times radical 7/3 and +2 radical 7/3 times -7/3. Okay? Keith.
Well, is it just a coincidence that it works out to be the opposite of
I was thinking the same thing. I'm going to go with coincidence because of the symmetry up here, that because it's x squared plus xy plus y squared, that the form of the derivative is really the same whether I take it with respect to x or y. And I think if we had a different shape, it wouldn't work that way. And I think this is, what is this, an ellipse? No. I can't figure out what it is. But I think it's a function of the shape, so no, I would not say that I was right. So
we'll have the same way if we use the original equation and use that was x squared times y squared, and then use the derivative of that and then put all the same calculations. Like would that just be a factor into that?
You did what?
Because x squared times y squared is x squared plus. Oh no, it's 2xy. Hang on.
Okay. Okay, so we good? All right, then I think I'm going to say that when we come in on Monday, we'll do a warm-up from the practice sheet. And I have one more example there that I want to do, but I think we will start 3.7 on Monday. Okay. And that'll probably take us Monday and Wednesday. Because the inverse derivative can go back, and those are shorter periods. Okay? So I will update the portal, and then we'll go from there. Okay? The homework, I think, is there, and you can start the homework if you wish, or when you wish. Okay, but I'll update the portal right now. All right, any other questions? Okay, then you can pack up and clean up your desks. Fiona, can you talk to me that about, oh no, you can't. Never mind. About the joint code? Oh, yeah. So you don't have the right code because you're in DC. Yvette, I'm going to send you a code that you need to use on the AP website, okay, to join the class officially. Fiona can help you get to the website, but her code is different because she's in DC. But I'll send that to you later today, all right?
Okay, thank you.
Okay, thanks, bye.